talk about time series. So time series is measurements of the same thing over time. So they're indexed on time. What we have here is dates. So that's October 26, 2011. And this is the cumulative power. And what this column is it just subtracts the next day from the previous day to get the actual power generated each day. So I'll just show you what these look like. We'll do a little plot here. So cumulative power, how much power is generated by this. This is a bunch of solar panels. Excel figured out that this is time, and so it nicely can change what is showing on dates, kind of adjusting as we go. So cumulative powers, it's fine. You can see that overall there's an uptrend, and we can see that there's cycles. But if we look at this column, so I'll take column A and column C. Now we can see that there's a very clear seasonal pattern, or it's really a cycle, and it goes from the beginning of the year, so like January, where the production of these solar panels is low, to peak time in the summer when it's high, and then back to December when it's low. So you see this very clear pattern. Obviously there's individual days where production is higher or lower, probably depending on things like weather, rain, whatnot. So this is what it looks like cumulatively over time, and this is what it looks like if we just look at the individual production by day. If I click on one of these values, I'm going to right click and hit trend line. This is the same thing we did for regressions, but now instead of doing a regression line, I'm going to do a moving average. What that's going to do is plot a moving average for me. Unfortunately, it plots it in blue, so we'll just switch that from blue to red, and I will make it bigger. So it's pretty crazy looking, because what it's doing is just showing the average of 2 days, so today, like yesterday and the day before. But watch what happens as we increase the periods. Right? They start to tone down. So now we're averaging the past 28 days. So a lot of the variation is gone. As we start to take in more time, they start to look much more like they're normally distributed. Right? So now we're taking into account the prior 68 days. So one thing you'll notice is that the kind of mean here looks like it shifts. So we'll go back down here to 40. So it kind of looks like the peak is right here. And as I increase this to, let's go to 70, it starts to shift over to the right. And that's because the more you have here, the more of a delay it has. So this becomes more of a lagging indicator. If we increase this a lot, so let's say we increase it to 3,000, right now it's looking a lot different than what the actual values are. And if we continue, is that as much as it'll let me go? So if you were to continue to do this, eventually it would become a straight line. So that would be like, because now if you continue to do it, it becomes just the average of all values. And so we already know what that looks like. It's a straight line. So the average, we could just calculate this, equals average of these numbers would be 11. So if we were to continue our trend here, we get rid of all the oscillations and it would just be a straight line at 11. Okay. So that is looking at the time series. We can see very clear cycle here, a yearly cycle goes low in the wintertime, high in the summer. That makes total sense given that these are solar panels, and the light is weakest in the winter in the United States and strongest in the summer. All right, so we could also do this with, instead of doing it visually, we could just say we have a moving average. And I'll go ahead and do exponential smoothing. I'm going to use the data analysis tool pack. And exponential smoothing, here's moving average. My input range is going to be here. And my interval, let's say we'll do the preceding 10 days. My output range is going to be here. All right. So if we plot these, I'm just going to delete those values. Let's do these together. Insert. That moving average line is the exact same thing that we saw here. In fact, if we change this plot, I'm running out of real estate here. So if I look at my trend line here, my moving average, and I look at it for 10, which it did in blue again, because Excel is nuts. I'll switch it to orange, that way it'll match even more. We'll make it thicker. Right, and then now it's, see, it switched from dash type to line. It's too thick. Right there. All right, so point is, these are exactly the same. Right. Exactly the same values that you get by using the moving average. Let me move. This one's the one we did previously, so we'll just get rid of that for a second. So this is calculating a moving average manually, and this is using the plot feature and trend line. Cool. Let's just add in exponential smoothing and do the same thing. So I'm going to go data analysis tool pack, exponential smoothing. My input range is here. My dampening factor is a value that I come up with. I'm going to say 0.5, and we'll look at how this changes. My output, we'll start here. All right, so the dampening factor is how much weight to put on prior values. Just going to delete these graphs, and we'll do a couple of these. So we'll say smooth 0.5. I'm just going to, this is going to be x smooth 0.1 and x smooth 1. All right, I'm just going to repeat this process but use different dampening factors. So instead here I'm going to do 0.1, and I want my output range instead of E to be F. Okay, and if I make my value 1, change this value from F to G. So the dampening value of 1 basically gives no value. Let's change it. That should be, we should be able to get a value for this. We'll do 0.9. I think we just had an issue with the way that there we go. So there are values, it just kind of penalizes the more it's slower to respond. And let's go ahead and plot these. Take all of them and make my plot. Okay, it looks a little wild. Let's go ahead and remove moving average. We'll remove the original data. So now we can just look at these differences. So when the exponential smoothing dampening factor is low, it is not penalizing prior values as much. And you can see the yellow line here, that's 0.1, it's really jagged, so it varies a lot. As the dampening factor increases, it smooths out. So it's taking into account more prior values. The dampening factor is giving it less of a penalty for old values. And we'll take this, we will turn back on our exponential, this is 0.5, so it's a halfway point. I will turn this one off. Okay. And you can see it has less volatility. Turn this back on. And I'll make it orange, but we'll make it transparent. All right, so you can see the light orange in the background is the low dampening factor. Red is the medium dampening factor, and blue is the highest dampening factor. So these are different ways of smoothing out the line depending on how much volatility you want to capture in your time series. Okay, so with all of these we were able to just use the Excel built-in data analysis pack to go in, kind of fill it out and tell it what values we wanted. The last one we'll do is using Excel stat. This will be ARIMA. Let's see, it's under modeling data, autoregressive moving average, time series is C, date values are A. These are parameters that you can pick. You don't have to really know what they are right now. So let's go with this. All right, it's completed, and it's given us the values that we have talked about. So we can see the mean squared error is 32. The root mean squared error is about 6. The MAPE, so that's our percentage error, is 59. These are other measures of goodness of fit. Here's the values that we put in, our constants. Here is the actual values, and here is the estimate. Right. So what we want to do is I'm going to take these, it predicted like way into the future. Our predicted values are on the side. I'm going to go to insert. We can see the ARIMA did a good job of capturing. It follows right along with the actual values. It's never going to be as spiky as the actual values, but it is closely following this. What we have way here at the bottom are the actual prediction values. So I'm going to move these over here so it's a little easier to see them. Oh dear. So you can see its prediction for the future is that little tail, which makes sense if you see the patterns like a hump, a hump, a hump, and then the model's predicting it goes back up. Okay, so there we did it. We did time series with exponential smoothing, moving average, and ARIMA, autoregressive integrated moving average, all very easily in Excel.